Hello, this is the demo for the project of robotics and AI. The title of the project is Distributed Transportation Tax Allocation in the Factory Automation Scenario. Uh, this is the introduction. The background of this project is in a factory automation scenario, and there are several uh, products and goods or goods with two sizes and small size and large size and need to be transported from the zone number 1 to zone number 2, and those are the assumptions I made in this problem. So all robots, they work in a synchronized way, so it takes one time slot for a runtime trip between zone 1 and zone 2, and all the goods arrived at the beginning of each time slot at zone 1. And there are 3 robots in total, and 1 small robot and 2 large robots. So the 1 small robot can only take the small products, and each one small product will take 1 unit space in the small robot. So the small robot has the maximum capacity of 4. And for the large robots, it can take small products and large product. And each small product take up 1 unit space, and each large product take up 2 unit space. So the maximum capacity for 2 large robots are 8. And for those 2 kinds of robots, the cost of round trip will take the small robot or 1 unit energy, and the large robot 2 unit energy. And the initial energy of the small robot is 100, and the initial energy for the large robot is 200. And those are the assumptions I made in this problem. And here the challenge is to design an algorithm that could deal with a dynamic transportation requirements and with the minimized energy consumption. So we want those robots to work for a longer time and transport more goods as many as possible. So for each agent here is the robots here. The environment is include the common task queue from the zone 1, and the other agents. Because, for example, for the small robots, the environment is the queue from the queue from the zone 1, and also the other 2 large robots is also part of the environment. And also the remaining energy is also regarded as the environment, because the agent couldn't directly control the energy it has. It could only be consumed. So here I propose an algorithm based on simple distributed algorithms and naive auction algorithms. So because this is a distributed tax allocation, there is no centralized entity to assign those tasks to those robots. So a simple distributed algorithm will be used here, and is called the leader election. So the basic idea is those 3 robots, they elect a leader to compute the task allocation, and then send it to the other robots, and they execute this allocation. So the first step is reach the agreement on the leader. So here is the first step of the algorithm, the leader election. So here each robot is keeping a popularity list of all 3 robots. And this list is used for balancing the energy, because computing those allocations consumes energy. So we want the three robots, they have a relatively equal chance to do those computations. So here is the algorithm. Each robot, they randomly select a least popular ones as their vote, and each robot broadcasts the vote to the other two robots, and then each robot receive the two votes from the other two robots, and if the votes they send are equal to the votes they received, so the three votes are equal, then that means they agreed on each other. So then each robot they update their popularity list and send the remaining energy to the leader and back to the loop. For example, in this figure here, the robot 1 send vote 1 to the other two robots, and the robot 2 and 3 they send vote 2 to the other two robots. So in this scenario, they couldn't agree. So the loop will not be break. So we'll goes to the next iteration. And in this scenario, all the three robots they voted 2. So in this scenario, they agreed on the leadership will goes to robot number 2. So they add value 1 to their popularity list, the attribute of robot number 2. So the next time they will create their votes from the number 1 and number 3 because they have less value of popularity. So in this algorithm, the algorithm will come out like a polled leadership. So each robot will have a relatively equal chance to be a leader. And so after they agreed on the leaders, the next step is to the leader will execute a simulation task auction algorithm based on the remaining energy it has just received from the other two robots. So first it will load a queue from the zone 1 like this, and when the queue is not empty, it will loop this auction procedure. Here I let the small robots has the highest priority because the small robots they only consume energy 1 for a back and forth task. So the small robots it only beat the small goods, and until its capacity becomes 0. So like this, the first task in the queue is a small good. So the small robot number 1 will beat this good, and its capacity will -1. And here the next step is the two large robots with more energy remaining has a higher priority. In this scenario, the robot number 2 it have energy of 98. Robot number 3 has an energy of 96. So robot number 2 has a higher priority. So this large goods will be beat by the robot number 2 and will reduce its capacity by 2. So after the previous step, each robot the small robots will only beat the small goods. The large robot will only beat the large goods. So after that, it will simulate the next step because the task exchange. The purpose is that to reduce the number of robots if the task could be finished by less than 3 robots. For example, in this scenario, before the exchange, the large robot number 3, it only have one large task in its load, but the small robot has 4 small tasks in his load. So here, if we can put those 4 small goods on this large robot, so the small robot doesn't have to take the action in the next time slot because those 2 large robots can perfectly finish those tasks, right? So this is the intuition, and the algorithm is if the remaining capacity of a large robot could accommodate the load of the small robots, the 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 load will be transferred from the small one to the large one. So after that, it will guarantee a minimum number of robots working uh, to further save the energy. However, yeah, there are some possibility that the load on a large robot is zero, like this. So because again, the small robot is a more energy efficient robot. So in this case, I didn't want those two tasks change their load to the large robots because it's waste 1 unit energy. And then the next step is auction the remaining task, because in step 2, the large robots only bid for the large goods. So after exchange, they can auction again, and here is the indifferent bidding. So large robots can also bid the small goods. So again, the small robots has a highest priority, and the large robots with more energy, it has a higher priority. So after that, the leader will send the simulation result to which is the assignment to the other two robots and execute the task. So each execution for a small robot consumes 1 unit energy. For a large robot consumes 2 unit energy. And here is my simulation. I also did a comparison group, and this group uses this kind of fixed assignment pattern. Again, the small robot has higher priority, and they also bid. No, it's not bid. They also will be assigned 4 small tasks. So the large robot number 1 has the secondary priority. It also will be assigned 4 large tasks. And the third large robot number 2, it has the third priority. So it will also be assigned 2 large tasks in maximum and 4 small tasks in maximum. So this is fixed. All those tasks will be assigned equal or more than or less than this number. Yeah, the task generation is another part of my implementation. And here I used a randomly select the length of the queue from 4 to 20, and the task type small large is also randomly select. And here's an example of a task queue. The 0 stands for a small good and the 1 stands for a large good. So two algorithms will use the exact same queue. And the initial values, the energy for a small robot is 100 and energy for a large robot is 200. And the popularity initially is all 0. And the termination condition for this algorithm is one of the robots has run out of the energy. So we will terminate the whole algorithm, the whole program. So because this scenario it has some kind of undetermined parameters, so I execute 5 times and get the average result. And here is the numerical results. The first one is the remaining task number in each iteration step. So I have the step 0 to step 100, and I did 5 experiments and take the average. And the blue line is the fixed assign, and the orange one is the auction assign. And we can see that the two algorithms doesn't have a huge difference in terms of the execution of tasks. So each of them can execute the task eventually. Yeah, the fluctuation is around the same number. When they are assigned a large number of tags, they will have a large number of tags remain. When they assign a relatively small amount of tags, they will have relatively small tags remain. And the next one is the total remaining energy of 3 robots. So I made a summation of the energy of 3 robots, and also the blue one is the fixed assign, the orange one is suction assign. So for the along this iteration step, the total remaining energy becomes it decreases as the iteration step becomes larger, because each back and forth will take energy. And in this figure, we can see that the auction-based algorithm can save some of the energy compared to the fixed assignment. And also, for each experiment, the fixed assignment always triggers the termination of the code. So here is the discussion. The proposed algorithm could save some energy while maintaining a good execution of the task. And here, I think maybe because the task generation is based on the random selection, and the energy parameters may not good enough to show the efficiency of the algorithms, because the task generation is not really dynamic in a large range. So maybe there are some future works to do. I probably will be build a more dynamic task requirements that's really in a large scale, so that could show how the algorithm can handle those dynamics in a good way than the fixed one. And yeah, and a more scientific energy parameters for this problem. Thank you.